by dynamical and statistical approaches.
Yeah.
Yes,
Thank
please.
you for the introduction. It's my great pleasure to be here today to tell you about the dynamics and statistical properties of these exoplanetary planets. And these are planets outside of our own solar system. And we're going to use the dynamics and statistical tools to try to learn the formation and the origin of these kind of systems. So first, let's start with our own solar system planets. So over centuries, until about 30 years ago, they are the only planets that people know around us, and they have been studied extensively. And now it is well known that they have very interesting architectural properties. In particular, we know that the planets have quite near circular orbits, and the orbital plane are quite well aligned, aligning with the direction of rotation direction of the host star, our sun. In addition, we can see that there are interesting properties where the giant planets are quite far away from the host star, while the less massive planets, the rocky ones, are much closer in. So inspired by these architectural properties, formation mechanism of planetary systems have been developed. According to this classical picture, the star and the planets all form in a giant molecular cloud, which collapses due to its own gravity. And as it collapses, it conserves angular momentum and forms a flattened disk, from which the planets form. And this way, due to the dissipation inside the disk, the planets have very low eccentricity orbits near circular, and there's no large inclination oscillations or excitations. So this way, naturally, people will expect the planets to have well-aligned orbits, which is similar to the direction of rotation of the host star, which is set by the preferred direction of rotation of the giant molecular cloud. And in addition, according to this classical picture of planetary formation, the planetesimals, which are the building blocks of these planets, are very different depending on the distance between the objects, the planetesimals, from the sun. When they're closer in, it's hotter and it's more rocky, and when they're farther out, it's more icy, it's colder. And the icy materials can stick with each other more efficiently, so they can build these higher massive planets as we see today. So according to this picture, the giant planets naturally form farther out, outside of this snow line, and these smaller terrestrial rocky planets are formed closer in.
Excuse me. When you talk about icy planet, what ice? What is made of?
That's a very good question. So actually, this snow line has different locations depending on chemical composition. It has the water ice line around it, and also like carbon dioxide snow line. And from these different locations, one can actually trace the different chemical evolution around this disk. And this is actually a very frontier research area right now to see how the chemicals evolve inside the disk. And here, most of the time, people consider the water ice line in this picture. So today, there are thousands of exoplanets discovered, and they show very different characteristics that revolutionize understanding in the architectural properties of the planetary systems. And how do people detect such systems? These planets are very faint. They mostly reflect the stellar light or have very weak thermal emission from themselves. So it is very difficult to detect these planets from direct imaging. So most of the planets are detected by carefully measuring the properties of the host star and inferring the properties and existence of the nearby planets. One of the earliest methods to detect these exoplanets is the radial velocity method, where in this picture, the planet and the star orbit around each other, around the center of mass. So if the orbit is slightly misaligned along the line of sight, one could see that the star can move away from us for a while and move towards us for a while. This motion can be detected from the Doppler shift, from the light emitted from the star. So if it is moving away from us, the light is red shifted, and if it is moving towards us, the light is blue shifted. And from this Doppler shift, one can tell the unseen smaller mass companion. And from this, one can also learn a lot of interesting properties of the planets. First of all, the amplitude of this Doppler shift depends on the planet mass, relative planet mass to the stellar mass. And in addition, the time dependence of this Doppler shift can tell one the eccentricity and the period of the planetary orbit. Using this method alone, how many planets have we detected? So far we've detected almost 500 planets using this radial velocity method, with the first one detected only in 1988. So there's a rapid growth of the planets detected every year using this radial velocity method. Another very popular, commonly used method to detect these exoplanets is the transit method. So in this picture, also the planet orbit around the star, and if the planetary orbit is lying directly along the line of sight, like this, one could see the planet cross in front of the star. And this way the planet will block an area around the surface of the star and cause the total brightness of the system to be reduced. And due to this periodic dimming, one could tell the existence of this planet. So what properties of the planet can we learn from this method? First, from this amplitude of this dimming, one can tell the relative size of the planet to the star, which is proportional to the size of the planet to the star. And secondly, from this time dependence, one can also tell the eccentricity and the period of this orbit from the periodicity of this transit. And then using this method, there are almost 2,500 planets discovered to today, with the first one detected only around 2000, the year 2000. So this is largely thanks to the space-based mission Kepler, which mainly detect these transiting exoplanets. So what can we learn about the architecture properties of these systems? So here we're putting the planets with the different detection methods together in this eccentricity versus orbital period plot. And immediately we can see something very striking. First, we can see that there are planets with very short orbital periods, with periods even less than 1 day. So they're orbiting the whole star very fast. And this is much faster comparing with our own solar system planet, where the innermost planet, Mercury, has an orbital period of around 88 days. What's more puzzling is the mass of these kind of planets. Some of the planets with these very short periods have mass quite large, reaching even above the mass of Jupiter. And this greatly challenges the classical planetary formation theory, because there are not enough solid material very close to the host star to form this very giant planet. In addition to this orbital period, there are also striking features in this plot, where there are planets with eccentricity higher than 0.9, comparing with the near-circular planets in our own solar system, such as the planet HD 80606b, which has an eccentricity higher than 0.9, and this looks drastically different from the circular orbits. So how do this eccentricity get excited to produce this kind of planets? In addition to this eccentricity and semi-major axis, these clever observational techniques can also help us determine the very detailed features in the architecture properties of the planetary system, such as the spin-orbit misalignment, which is a mutual inclination between the planetary orbit with the direction of rotation of the host star, as represented by the red psi angle here. And what is the method to detect this angle? This is based, one of the methods to detect this is the Roster-McLaughlin method, and this is based on the transiting systems, where the planet crosses in front of the star. In addition to produce the dimming in the brightness of the host system, it can also produce the net Doppler shift for the system. So for most stars, the stars are rotating. So half the star is approaching us and the other half is receding from us. As the planet orbit across the star, it will block either the approaching side or the receding side. And this will leave a velocity anomaly for the whole system. And if the planetary orbit is aligned with the stellar spin axis, one would see the velocity anomaly to be symmetric as a function of the transit time. And when the planetary orbit is misaligned from the stellar spin axis, one would see the velocity anomaly to be asymmetric. And from this asymmetry, one can tell the sky projected spin-orbit misalignment. Okay, so using this method, there are around 70 systems with the spin-orbit misalignment measured, as shown in the histogram plot here. And we can see that there are systems with very large spin-orbit misalignment, reaching around 90 degrees, or even approaching this 180 degrees. And this is very different from our own solar system with the misalignment very small. And this also challenges the classical picture of planetary formation, which says that the planetary orbit should be quite well aligned with the spin axis of the star. So now the pressing question is, what's the missing chapter in the basic classical planetary formation theory that can give rise to this variety of the exoplanets with these very puzzling architectural properties, different from our own solar system, which is so ordered and flat. So in this talk, first I'll discuss the interesting hierarchical three-body dynamics, which can naturally give rise to these misaligned systems. And then I'm going to discuss some statistical results on the circumbinary planetary systems and infer the origin of such systems, which are planets around stellar binaries, to see how they differ from planets around the single-star systems. So first, what is a hierarchical three-body system? It is a system where including three objects, and two of them are very close to each other, and the third one is very far away. So this kind of system is quite stable, and one can treat it as an interaction of two binaries, where the inner binary is composed of the inner two objects, and the outer binary is composed of outer object orbiting around the center mass of the inner two objects. So there is a distinct timescale difference in this model, where the orbital timescale is much faster than the interaction timescale. This way one can average out the orbital motion by smearing out the mass along these orbits and consider the interaction of these two orbital wires, or these secular effects. And basically, the outer orbit can extract angular momentum of the inner orbit and also torque the inner orbit to make its inclination vary. So these hierarchical three-body interactions has been studied earlier on in the literature in 1960s by Kozai and Lidov independently, who were focusing on the solar system dynamics, with the outer perturber, typically the planets in the solar system, have near circular orbit, and one of the inner objects, the satellites, or the natural satellites, or the artificial satellites, can be approximated as a test particle. In this case, when one expand the Hamiltonian in power series of the semi-major axis ratio, it's been found that the third power expansion, the octuple level, can be averaged to 0. And the quadruple level, which is the ratio to the second power, is a very good approximation for the dynamics. And in this test particle regime, the outer orbit is stationary, so it can be reduced to a 3-degree freedom. And when one averages it out, considering the secular dynamics, it can be reduced to a 2-degree freedom. Depending on these four canonical variables, the angular momentum conjugated with the argumentary axis and the z-component angular momentum conjugated with the longitudinal node, where these two angles specifies the orientation of the orbit, where the argument pericenter of small omega determines the orientation of the orbit in this orbital plane, and the big omega determines the orientation of the orbit in this reference plane. So here is the expression for the particle level energy function. Immediately you can see that this is independent of the longitude of node, indicating that the z-component angular momentum is a constant. And this tells us that this combination of electricity and inclination is conserved, this is the z-component angular momentum. And this can be understood intuitively as the inner orbit is in an axisymmetric potential. It has also been found that when the mutual inclination is over 40 degrees, the eccentricity and inclination can oscillate with large amplitude. And this can be seen here in this plot, which plots the eccentricity and inclination evolution as a function of time. We can see that starting with almost zero eccentricity, the eccentricity can excite to large values, and inclination can also oscillate. So recently, inspired by these exoplanetary systems, people have studied, focused more on the case when the outer orbit is eccentric. In this case, the octuple term cannot be averaged to zero, and this plays an important role in the dynamics of the system. And we can see, including the octuple level of expansion, it also depends on the longitude of ascending node, so the z-component angular momentum is no longer constant. And this is different from before, where when the z-component angular momentum is a constant, the orbit cannot flip to cross 90 degrees, which will cause the z-component angular momentum to flip sign. And including this octuple term, the inner orbit can flip across 90 degrees. And also the eccentricity not only can be excited to large values, it can be excited very close to unity. So what does this tell us? This tells us that if we have a planetary orbit that is initially quite well aligned with the stellar spin axis, and due to the perturbation from a misaligned companion, the inner orbit inclination can vary, and this way can produce a large spin of misalignment. But there are some limitations, starting with a high inclination and produced by this perturbation from the outer companion. In particular, to excite eccentricity and have inclination oscillations, the companion needs to be quite largely misaligned, larger than 40 degrees, as shown previously in the literature. In addition, people have found that the final inclination, even including the octuple case shown in red, is quite well constrained between 40 to 140 degrees. So it shows that there's a limitation in the final spin of the misalignment that can be produced through this mechanism. So is it possible to produce the full range of spin of the misalignment, even up to 180 degrees, as shown in the observation? So to test this, we put the companion in a near coplanar frame from the inner test particle and see what will happen. Intuitively, nothing very interesting will happen, because when the mutual inclination is low, the torque from the outer companion is also smaller. But to our surprise, we find that if the inner orbit has a high eccentricity larger than 0.6, the inner eccentricity can further be excited very close to unity, and inclination can be flipped to about 180 degrees. And this is shown in the figure here, where the upper panel plots 1 minus eccentricity as a function of time, and the lower panel plots inclination as a function of time. So you can see that inclination stays quite low, around 0 for a while, and then have a sudden flip. And at the same time, the eccentricity starting quite close to 0 can be excited even up to 1 minus 10 to the minus 5 or even 6. So why is it interesting? It's interesting because the pericenter distance is proportional to 1 minus eccentricity. So as eccentricity can be reduced by orders of magnitude, it means the pericenter distance can be greatly reduced, and the inner two objects can be brought very close to each other. And this way, it can help with the migration of the planets, forming initially quite farther out and be brought closer, to produce these hot Jupiters. And secondly, we can see that inclination can be flipped by 180 degrees, so they can help produce these largely maximally misaligned objects with spin-orbital misalignment up to 180 degrees. So exactly how do the orbits flip? To illustrate the flip, I include a movie here for starting with the low inclination. For simplicity, we use the test particle here. So the outer orbit is stationary, and I put the outer orbit in this xy plane. The colored ring is the inner orbit, and the inner test particle will orbit very fast along this colored ring. And here we're just showing the secular effect with the average of the while. And you can see it's starting very close to the orbital plane of the outer perturber, so it's lying very close to this xy plane. The black arrow shows the direction of the inner orbit, and the pink arrow shows the z component of the black arrow. So when the pink arrow flips sign, it is a time when the inner test particle orbit flips. So are you ready for the movie? Okay, I take it as a yes. So you can see that due to the perturbation of the outer companion, the orbit precesses very regularly. The inclination oscillates with small amplitude, and it just flipped. And now it's precessing back. And I assume you want to see it again. Yeah. You may also notice, if you look very carefully, that the eccentricity increases monotonically before the flip, and then decreases monotonically before the flip.
So to get this set up, you need the outer plane to be very eccentric.
No, you don't need the outer plane to be very eccentric. It just doesn't, it cannot be exactly zero. So the octuple term is proportional to eccentricity, outer eccentricity over 1 minus outer eccentricity squared. We just need that term not to be zero. It's a combined effect of the semi-major axis ratio and the outer eccentricity. It can be 0.1, 0.2, it's fine.
But there's no constraint on this misalignment for the outer.
Yes. So actually, there is a constraint on the mutual inclination, and then for the coplanar flip, we will later on see that it's very regular. So we obtain the analytical criteria for the flip that depends both on the inner eccentricity, mutual inclination, and the theoretical parameter. That's a great question. Okay. So how about the high inclination flip, starting the mutual inclination at higher values? So similarly, we use the test particle approximation, and this colored ring is the inner orbit. The outer orbit is in this xy plane, and then the arrow shows the direction of the orbit. So now we can see that the dynamics looks more complicated. It has roughly 2 time scales. One is the faster precession time scale, and the other is the flip time scale. And we can also see that eccentricity oscillates before the flip, different from the case of a low inclination. So what is the underlying resonance that caused the flip and eccentric excitation? So to study this, we look at the surface of section of this system, which can project its higher dimensional 4-dimensional phase space to a 2-dimensional surface by intersecting the trajectory with this surface. And there are different dynamical regions in these surfaces that can tell us the underlying dynamics. In particular, there's this resonant region where the points intersecting the surface fuse the 1-dimensional lines. And this conjugate coordinate angle is bounded, and these are the resonant regions. And the trajectories here are quasi-periodic. And there are also points that feel higher dimension, and these are the chaotic trajectories. So plotting the surface of section corresponding to the coplanar flip trajectories, you can see that they look very regular, and this is in the resonant region, and it corresponds to the libration of this longitude of pericenter, which is the direction of the pericenter of the inner orbit. So in this physical space, you will see, if this is the test particle orbit, you will see it librating around this 180 degrees unparalleled with the pericenter of the outer orbit. And this chaotic point corresponds to the trajectory starting with a higher inclination. And this is actually, the chaos is due to the overlap of the quadruple resonances and optical resonances. And we found the diagonal time scale to be quite short, around 6 of this quadruple oscillation time scale. So this explains the difference between the low inclination flip and high planet. Now let's look at the analytical expression for the flip criteria. So we've seen that it looks quite regular. So is it possible to obtain some analytical understanding of the flip? So to study this low inclination case, we can approximate the Hamiltonian to the low inclination order. We took the first order inclination and found that in this case, the Hamiltonian can be simplified to a 1-degree freedom system. And this immediately tells us that the system is integrable. And here's the equation of motion of the eccentricity and the conjugate in longitude, the pericenter. We can see the eccentricity only depends on the optical terms. So this explains that in the low inclination regime, the eccentricity do not oscillate at the quadruple order. And we can also solve for the flip time scale and the flip criteria and obtain an analytical expression for the flip time scale and flip criteria. The flip criterion is shown here. The flip time scale is more complicated, so I don't include it in the slides here. The flip criterion tells us the theoretical parameter needs to be larger than this function in order for the test particle orbit to flip. And basically it's saying that it's easier to flip the inner orbit if the eccentricity is larger. And this makes sense intuitively, because when the eccentricity is larger, the angular momentum is smaller, so it's easier to flip the orbit. And it's also easier to flip the orbit when the longitude of pericenter is around 180 degrees, meaning the inner and the outer orbit pericenter are exactly anti-aligned. And this is the case when the interaction is stronger, when the torque is stronger. So how does it compare with the numerical results? So you can see, starting with a mutual inclination of 5 degrees, it agrees very well with the numerical results, with the black lines are the analytical expression, and then the colored crosses or pluses are the numerical results for both the flip criterion and the flip time scale. Okay, so how does this produce the counter-orbiting planet? So we have a planet initially aligned with the spin axis of the host star, and due to the perturbation of the outer companion, the orbits will oscillate and flip. During the flip, the eccentricity got excited, so the pericenter distance got reduced. What will happen when the pericenter distance gets reduced? So when the objects get very close to each other, when the planet and the star become very close to each other, the tidal interaction is very strong, as the tidal interaction is proportional to distance to the 6th power. And when the tidal effect takes over, it can circularize the orbit and shrink the orbits and stop the orbits from flipping back. And this way will end up with a counter-orbiting planet and with a very short orbits around the host star to produce this maximally misaligned planet. And here is the numerical result. So the first panel plots inclination and spin orbit misalignment as a function of time. And the middle panel plots 1 minus eccentricity and semi-major axis as a function of time. So you can see that during the flip, eccentricity become very high and 1 minus eccentricity is very small. The pericenter distance got reduced, and orbit then got shrinked, and eccentricity got circularized. And this way, in the end, we have a hot counter-orbiting planet around the host star.
In all your analysis, why don't you include the masses of these planets?
Yeah, in principle we could, but this is a good approximation because the planet mass typically is very small comparing with the sun, with the star. And if the perturber is a star, one can approximate the mass of the planet to be a test particle. For Jupiter, the massive one is about 0.001 times the mass of the star. So and then for the Earth is 3 times 10⁻⁶. So that's why it's a good approximation. However, it's also important to consider the mass of the planet if the perturber is massive. And in fact, for the analytical expression that I show, it's a test particle approximation, which makes the analysis simpler to obtain this criteria. However, it is being done considering the mass of the planet and then considering all different mass of the perturber to have a more complete picture. So thank you. And then including when the test particle is more massive or the perturber is less massive, sometimes the flipped criterion is not robust. It needs a stronger perturber to flip the orbit. Yeah, thank you. Okay, thanks. Thank you. Yeah. Now we can have other interesting applications for the this hierarchical three-body dynamics. And this mechanism has a wide applications because it can apply to many hierarchical three-body systems, including the supermassive black hole binaries. Because as the two objects
comes from computation? Is numerical calculation?
Yeah, I think this is a numerical simulation. Yeah, the credit is from NASA. We're now trying to look at the inner edge of Sagittarius A, the supermassive black hole in our backyard, our Milky Way galaxy. And it will be exciting to imaging around it. And for the supermassive black hole, we're very far away from imaging the direct systems. Anyways, it also has exciting application to stars around supermassive black hole binary. And supermassive black holes are very common in the center of galaxies. And the galaxies interact with each other and evolve. And as they merge, they will also bring a black hole with them. And the black hole will sink to the center of the merged galaxy and form these supermassive black hole pairs. And at a large distance, at this kiloparsec, which is around kilo light years, this kind of supermassive black hole pairs have been directly imaged. And at shorter distance, it's very difficult to resolve these scales to direct imaging this supermassive black hole. Okay, so it's important to use these dynamical mechanisms to prove the properties of these closely separated supermassive black hole binaries in galactic center. And for the hierarchical three-body interactions, it can change the profiles of stars around the supermassive black hole, which can help determine the existence and properties of the supermassive black hole binaries. So here we're considering stars orbiting the primary supermassive black hole and the perturber can excite orbits. And as the star being brought very close to the supermassive black hole, the tidal field of the supermassive black hole will stretch the star. And when it's very close, the stretching force will balance the self-gravity of the whole star and can stretch the star apart. And this will produce the tidal disruption event. And this is a powerful mechanism to prove the properties of the supermassive black hole, which otherwise do not emit light for this dormant supermassive black hole. And this hierarchical three-body mechanism is very powerful in generating these events, as we've seen that the maximum eccentricity can reach 1 minus 10 to the minus 6. This means that even when the star is at 1,000,000 times the tidal disruption radius, the standard tidal disruption radius, the pericenter can still be brought very close to the supermassive black hole around the tidal disruption radius for the star to be disrupted. However, we need to be very careful calculating the tidal disruption rates, because as we've seen that the eccentricity excitation are due to resonances, and if the orbit precesses, the resonant angle is no longer liberating and eccentricity excitation will be suppressed. And for stars around the supermassive black hole binary, the general relativistic precession and then the Newtonian precession due to the stellar system self-gravity can cause the stellar orbits to precess in a comparable timescale with the causality of vibration timescale. And in these conditions, the eccentricity cannot be excited. So for the galactic center, we run numerical simulations to calculate the final tidal disruption rate and the change in the stellar profile. And we found around 6% of the systems get tidally disrupted, and 70% of them get scattered away due to the perturbation from a supermassive black hole companion. And these scattered stars can change the stellar density profile around the primary supermassive black hole, because for stars that are largely misaligned with the supermassive black hole binary plane, they are more likely to be scattered away or be disrupted. So what's end up is a shape of a torus around the primary supermassive black hole. And normalizing with the number of stars around the primary supermassive black hole, we found the tidal disruption rate can reach 10 to minus 3 per year. And this is order of magnitude larger than the stars around a single supermassive black hole. So for the theoretical three-body dynamics, we've seen that coplanar flip can produce the counter-opting systems, and the theoretical three-body dynamics can also enhance the tidal disruption rates. So for the next part, I'll discuss quickly about the planets around stellar binaries in another configuration. So far we've considered planets orbiting a primary star and the other star is a perturber. And it's also possible for the planet to orbit around the stellar binary, and these are the so-called circumbinary planets. And this is a common theme for science fiction, such as Luke Skywalker's home planet, Tatooine. So do such systems really exist in our universe? Thanks to the detection of these transiting planetary systems, there are 9 transiting circumbinary planetary systems recently discovered, with the first one discovered only recently in 2011. And now there are also systems orbiting the stellar binary discovered where the planets living in a habitable zone. So it's possible in the future we'll find possible aliens living very close to the stellar binaries instead of single stars. So what are the differences between the stars orbiting a stellar binary with the stars orbiting a single star, with the planets orbiting the single star? And how do this circumbinary planetary system form? So to look at this, similar to studying the planets around a single star, we can first look at the architectural properties of the circumbinary planetary systems. So different from planets around a single star, there is a unique length scale involved in this circumbinary system. That is the stability limit, within which the planetary orbit is in general not stable. So according to different planetary formation theories, it will produce different outcomes around this stability limit. If planetary migration is very important, is dominant, where the planets form farther away and all migrate closer into the star, similar to the ways to produce the hot Jupiters, then the planets will stop near the edge of the protoplanetary disk where the planets form, and the inner edge of the disk is determined by the stability limit. So in this case, if migration dominates, then one would expect to see a pileup of planets very close to the stability limit. However, if the planets just form in situ without moving around too much, and if scatter is important after the migration, one would not expect to see this pileup of planets near the stability limit. What does the observation tell us? Do you want to guess? So the observation tells us that there is likely a pileup near the stability limit, as shown in the face-on figure here, where the blue line is the scaled planetary orbit to the stability limit, and the gray region is the instability zone. But this can be a selection effect, because it's easier to detect the planets very close to the instability zone. So is it a selection effect? So to study this, we use the hypothesis testing, where we assume that semi-major axis of the planets follows a distribution without a pileup. And if we can reject it, it shows that it's likely a dynamical pileup. If we cannot reject it, it's likely a selection effect. And to test this hypothesis, we use the Bayesian method by calculating the probability that the semi-major axis is smaller than the observed value, requiring it to transit at least twice. And this condition takes into account the selection bias, the selection criteria. So here is the result. So we use two prior distributions according to the systems around a single star. The first is a uniform distribution in the semi-major axis from the transit surface. And the second one is a parallel distribution from the radial velocity surface. So the probability density function for the average semi-major axis to the stability limit ratio is shown by these two colored lines with these two different prior distributions. The black line is the observed value. So you can see that the probability to be smaller than the observed value is quite large. It's around 8% to 14%. So you cannot reject the null hypothesis. And it is likely that the semi-major axis of the circumbinary planets is consistent with the distribution of the single star system. And get back to the formation mechanism, it's also likely that the migration does not dominate, or there are scatters after the migration of these planets. Another interesting feature of the circumbinary planets is the complementarity of the planetary orbits around the stellar orbits, where this shows the edge-on view of the stellar orbit and the planetary orbit. We can see that roughly the planetary orbits are quite well aligned with the stellar orbit. But this also might be a selection effect, because it's easier to detect the transit of the planets if the planetary orbit is aligned with the stellar orbit. Because for the stellar orbits, they are all the eclipsing binaries where the stars transit across each other. So similarly, we test whether this is truly a coplanar configuration. And we assume this neutral inclination follows a three-dimensional Fisher distribution where the kappa characterize how aligned the planetary orbits are. When kappa is 0, it's more isotropic, and when kappa is larger, it's more aligned. And we found that we can reject the null hypothesis for kappa smaller than 500. And this shows that mutual inclination for these systems are likely less than 3 degrees. And interestingly, this average mutual inclination is the same for multi-transiting planetary systems around a single star. What does this tell us about the formation of these cartoony systems? So from observations, it's been found that the protoplanetary disk, which is a disk that formed the planets, and the debris disk, which are the protoplanetary disk when the gas got blown out, are mostly quite well aligned with stellar binaries. So this way, when the planets form naturally inside the disk, one would expect the planetary orbits to be quite well aligned with the stellar orbit, assuming that there's no strong interactions between the planets to excite the inclination. So it's likely that these circumbinary planets are formed quite dynamically cold for these transiting samples that we detect. Okay, we can also get a very interesting result on the occurrence rate of circumbinary planets. So before in the literature, it's not clear whether, it's not known whether the planetary orbits are coplanar or not. And it's been found that if they were coplanar, the occurrence rate of the circumbinary planets would be similar to that around single stars. And if the planetary orbits are largely misaligned, the occurrence rate of the circumbinary planets would be much larger than that around a single star. And now we know it's the first case scenario. So the circumbinary planet's occurrence rate would be similar to that around single stars. So the efficiency to produce these closing planets is quite similar for both the single star systems and the stellar binary systems. Okay, so what will happen in the future? Now we already have thousands of planetary systems discovered outside of our own solar system. What will happen next? So next, currently with the detections mostly found by Kepler, we're looking at a single direction quite far away from us, about a kiloparsec or kilo light years away from us. And now with the test mission, which will launch next year, by the summer next year, it will look closer around us with this 4Pi full sky survey, and will monitor a large number of stars and look at the bright systems, which will be easy to do follow-up observation to detect the atmosphere and the planetary companion of those systems. And they will catalog more than 1,500 candidates very close to us, and including possibly 500 Earth-sized or super Earth-sized planets, will help us learn more about the formation of these planetary systems and detecting possible habitable planets. And happening after that, furthermore, in about mid-2020, WFIRST will launch, and they will include a microlensing exoplanet survey, looking at a slightly different parameter space. So currently, with the transit method and the radial velocity method being the most dominant methods to detect these planetary systems, we're favoring the planets with short orbital periods. So now there are not many Jupiter or Saturn analog, exoplanet analog detected. And WFIRST will include the microlensing exoplanet survey. And this is able to detect planets up to like 10 AU or even hundreds of AU with mass reaching below the mass of the Earth. And this way it will give us a more complete picture of these exoplanets and tell us more about the formation and habitability of planetary systems. So with that, I'll end here, and I'll leave the summary slide here and take questions. Thank you for your attention.
Questions? Comments?
Well, 25 years ago, there was a thesis, PhD thesis, about 5 bodies. In finite time, one body would escape to infinity. 5 bodies interacting by Newton's law. One of the 5.
5 systems with a neutron star in the center?
Not neutron star, just ordinary planet.
I see. That's really exciting. So it's a study of the...
One body escaped in finite time.
That's very exciting. Actually, it's an analog to our own solar system. Recently, especially done by last time, his collaborators, they found Mercury actually has a high probability to escape from the solar system in finite time as well. So it's possibly a very similar analogy. So for the 5-body system, are they? So it's a detected exoplanetary system?
No, they proved that such a thing exists.
So they proved for 5-object system, one will eventually escape?
It could happen for some condition. So I wonder whether it can be observed or not.
That's a very good question. So for what kind? I think for this.
I think it's actually symmetric. Actually, 2 of this body goes away, 1 body goes in.
2. So they have 5 planets.
Yeah.
2 of the planets will go farther out, and 1 planet will
move away.
Move away. So it's due to the interaction of the planets themselves.
Yeah.
I see. I think there are some observational consequences where people can probe this kind of scenarios. In particular, this microlensing service, it can detect free-floating planets. And I assume for these ejecting planets, they may have a different velocity relation. And it's possible to find these free-floating planets, but to tell the origin of these planets might be tricky, because there are many ways where the planets can be ejected. First, just from the planetary interaction, as you mentioned, in these 5 planets systems, the planet can interact with each other and eject. And also for these planetary systems, they are not isolated. They have stellar companions, and they are living in the neighborhood with the stellar encounters. And these stellar encounters can also eject planets out. So with the microlensing survey, it's possible to find this free-floating planet. But it will be a very exciting question, very interesting one, to tell the origin of these free-floating planets, whether it's being ejected through the planetary interactions like a 5-body system, or just the ejection from a stellar encounter. But definitely, for our own solar system, there are a couple of interesting stories telling first Mercury may be ejected, and possibly there were 5 giant planets initially in the solar system, and one of them got ejected. And okay, I can go on for a long time. Yeah, I think this is definitely a very exciting.
It should be interesting because the thesis got a big award, I think, but then I think some people question whether the proof is correct. It would be nice to actually see.
Sorry, I'm not aware of this paper. I am aware that there are studies about the interaction of planets, and they found for a system with 2 planets is analytical. You can find the distance where it's stable. It's about like some fraction times the Hue radii, where it's larger than that it's stable, closer than that it's unstable. And for 3 objects, it's becoming more complicated. And now using numerical simulations, they found this instability time scale as a function of the spacing for 4 or 5 systems. And they found that beyond 4 or 5 systems, it behaved qualitatively similar to the 4 or 5 systems. But yeah, it will be very exciting to look at the 5 system that
Maybe you can do a numerical calculation. Maybe you can do a numerical calculation to see.
Yeah, exactly. I think now the general approach for the 4 or 5 object interaction is numerical. Yeah, exactly.
So how typical is the architecture of our solar system in the all the discovered types of planets?
Yeah, that's a very good question. Actually, the sample is not very complete. As you will see, like most of them is quite close to the star. And from the macro lensing service, although they don't have a strong sample, I think it's just it's around like 50-50-ish. It's like half similar to us and half different. It's not very unique. But the uncertainty is very large. And definitely with W1st, they can tell more about this architectural properties of the solar system. And a lot of the detected systems, because of selection bias, they detect these very compact systems. Very close.
So, by the way, why do you say the Mercury may escape? Why do you say Mercury may escape?
So this is the numerical study by Lascar and his co-authors, and they found from the numerical simulations, if they involve our own solar system beyond billion-year timescale, Mercury has a large probability to escape. And the physical understanding is this: Mercury has a very small mass, and when the planets interact with each other, they tend to reach the equilibrium in angular momentum deficit. So. And since Mercury has a small mass, it's easy for it to require high eccentricity during the encounter with the other planetary companion. And eventually, Mercury is the poor, unfortunate planet having the less mass being injected out.
1 billion years long enough.
Yeah, more than billion years, yeah. But before the sun got large enough to possibly engulf us. So.
More questions? If not, let's thank Gongji again.
I think it would be better if you like this piece in terms of circular classes and then